All right, let's get into it. Today, we're going to be cosmic detectives. Our mission? To figure out what the entire universe is actually made of. It's a journey that starts with, well, everything you can see and touch, and ends with just 3 incredibly tiny particles.
So here's our game plan. First, we're going to track down the ultimate building block of everything. Then, we'll crack it open and see what's inside. After that, we'll figure out how these tiny pieces give an element its identity, see where they all live, and finally, we'll meet some atomic doppelgangers. Sound good? Let's dive in.
Okay, first things first, we're on the hunt for the one single thing that everything else is made of. And that hunt really starts with the biggest question you can possibly ask. What are you made of? What am I made of? What about the stars, this screen? What is all of it fundamentally made of? That's the mystery we're here to solve.
Our very first clue is a simple word, matter. It's really just the scientific term for, well, stuff. Anything that has mass and takes up space. Whether it's a giant planet or a tiny speck of dust, that's matter.
To really get this, think about a house for a second. A house is made of walls, right? And those walls are made of bricks. So the brick is the basic fundamental unit of that house.
Well, in the exact same way, all that stuff, all that matter, is also made of fundamental building units. And we call those atoms. This is it. This is our prime suspect, the ultimate building block we've been looking for.
And that's the big takeaway for this part. The atom is the basic unit that everything is built from. So you could say case closed on what matter's made of. But believe me, our detective story is just getting warmed up.
So, what's the next logical step for any good detective? We found the atom, now we need to look inside. What is it hiding?
You know, for a very long time, scientists just figured atoms were these tiny, solid, unbreakable little balls. But then, in 1909, a scientist named Ernest Rutherford did this incredible experiment and discovered something mind-blowing. The atom wasn't solid at all. In fact, it was mostly empty space, with an even tinier, really complex system hiding right in the middle.
And this brings us to the 3 subatomic particles that make up this system. Meet our cast of characters: the proton, which has a positive charge, the neutron, which is neutral, no charge at all, and the electron with a negative charge. Now notice the charges. The proton is +1, the electron is -1, perfectly balanced. But then look at the mass. Protons and neutrons are the heavyweights here. The electron, it's unbelievably light in comparison.
And to really wrap your head around just how weird an atom is, this analogy is perfect. All those heavy particles, the protons and the neutrons, they're all squished together in this super dense core called the nucleus. That's the pinhead. The lightweight electrons, they're way, way out, circling the field. What does that mean? It means atoms, and therefore everything, are almost entirely empty space.
Okay, so we've got 3 simple particles. How in the world do they combine to create everything from the hydrogen and water to the gold in a vault? It's time to crack the code. It's all about an element's identity.
And the secret? It's actually incredibly simple. It all comes down to one thing. How many protons are in the nucleus? We call this the atomic number, or Z, and this number is like an element's permanent, unchangeable ID card. If it has 1 proton, it is always hydrogen. If it has 6 protons, it is always carbon. 79 protons, always gold. It is the one thing that defines the element.
Next up, we have the mass number, or A. Now, this one's just a simple head count of the heavy particles. You just add up the number of protons and the number of neutrons in that nucleus, and boom, that's your mass number. That's it.
And here's how you'll see scientists write this all down. The big letter is just the symbol for the element. The number on the bottom left, that's Z, the atomic number, the one that tells you what element you're looking at. And the number on the top left is A, the mass number, which tells you the total weight of that nucleus.
Now, you might be wondering, okay, but what about the electrons? Good question. Well, for an atom to be neutral, to have no overall electric charge, the number of negative electrons has to perfectly cancel out the number of positive protons. So if a carbon atom has 6 protons, it has to have 6 electrons. It's all about keeping things balanced.
All right, so we found a home for the protons and neutrons. They're in the nucleus. But what about those electrons zipping around? Where exactly do they live? Let's go find their address. See, electrons don't just fly around wherever they want. They live in these specific orbits or energy levels, and they fill them up based on some very strict rules. The easiest way to think about it is like a tiny apartment building. The first floor, closest to the nucleus, is tiny. It can only hold 2 electrons.
Once that floor is full, they have to move up to the second floor, which holds 8. And here's the key thing to remember. That outermost occupied floor is everything. An atom is happiest or most stable when that outer shell is full. That one simple idea is pretty much the driving force behind all of chemistry.
And that brings us to the final file in our investigation. This one is a fascinating little twist, where we find out that atoms of the same element, well, they aren't always perfect twins. These atomic lookalikes are called isotopes. And here's the deal in plain English. Isotopes have the exact same number of protons. Remember, that's what makes them the same element. But they have a different number of neutrons. This means they have the same identity, but they weigh a different amount.
This example with hydrogen makes it super clear. Both of these atoms are absolutely hydrogen. Why? Because they both have one proton. But take a close look at the nucleus. The one on the left, which we call protium, has 0 neutrons. The one on the right, deuterium, has 1 neutron. Same element, different mass. That's an isotope.
Which leaves us with one last kind of mind-bending thought. The entire universe, everything, is built from just these 3 particles: protons, neutrons, and electrons. So what is the only real difference between the oxygen you're breathing right this second and a solid bar of gold? It's just the number of protons in the nucleus. Just a number. Something to think about, isn't it?